could you please start sharing?
Yeah. Thank you.
Next speaker is Navin Sridhar. Yeah. You can start.
Thank you. Thank you all for giving me this opportunity to present our recent work on possible persistent neutrino counterparts to fast radio bursts. So we all know from the recent Chime catalog that the properties of the one-off events and the repeated bursts are strikingly different in terms of the spectral bandwidth as well as the duration. This is an example waterfall plot that shows that the non-repeaters are very short in duration with a broadband typically, and the repeaters are typically wider with a narrower spectrum. And you can check our recent paper for a toy model to explain the dichotomy. So this is suggestive of more than a single progenitor for FRBs. Perhaps there are multiple progenitors giving rise to different kinds of different subpopulations of FRBs. And this is also supported through the host observations of FRBs. For example, 1809-16, as you all know, was found to be at a distance of 250 parsec away from the nearest toponymic region. A very young magnetar born in a toponymic region could not have traveled this far and still be producing an FRB. And FRB 20/20E was in the limelight because it was localized to a globular cluster, again, not indicative of a young magnetar population. So this older population, for example, like black hole X-ray binaries. Motivated by these observations, a couple of years ago, we constructed a model for powering periodic fast radio bursts through an accreting engine. So you just have a super Eddington accreting compact object, which is also jetted over here, for example, through Blanford-Stein-like process. And the repetition in the fast radio burst could be powered due to the various flares and reconnection events that are launched from the base of the jet, and this could turn into an FRB. We can look into our paper for more details. And the periodicity that is observed in, for example, 1809-16 and 1211-02, the 16-day and the 160-day periodicity could be attributed to the lens-steering precision could be attributed to the lens-steering precision of this jet axis along the line of sight of the observer. That was this model. And recently, FRB 1211-02 and FRB 1905-20B were found to be associated with a persistent radio counterpart, and this was found to be more luminous than a supernova remnant and more luminous than local star formation activity, and they are quite compact. For example, for 1211-02, it's less than a parsec in size, and it's believed to be giving rise to a very large rotation measure of around 10 to the 5 radians per meter square seen from these two sources. And this requires the persistent the source of the persistent radio counterpart to be baryon rich. So, coming back to accreting X-ray binaries, we have seen ULXs and X-ray binaries to be surrounded by their accretion disk wind and jet inflated bubbles. For example, this one is from the ULX in NGC 7793, and this is the galactic SS433 Manatee Nebula. And we know that these bubbles are inflated by accreting engines with different orientations. For example, the equatorial width is determined by the slower disk winds, and the length here is determined by the fast moving winds along the jet axis. Again, motivated by this, we constructed a model for of what we call hypernebula. So you have a hyper-accreting X-ray binary, which is accreting at several hundreds to thousands of even hundreds of thousands of Eddington rates. This is typically such Eddington rates are typically expected prior to common envelope mergers, and the kind of accretion dominated, and most of the accreted matter will be thrown out as outflows, which inflate very compact, extremely compact, sub-parsec scale bubbles around them. In this work, we followed the bubble, the inflated nebula over time, and calculated various properties of the nebula, including the number of particles that are injected into the nebula, the magnetic field strength inside the nebula, its radius, the expansion velocity, and so on and so forth. As you can see, the nebula radius, after some time, it just saturates to a parsec, which is about the size of the persistent radio counterpart seen around 1202. And in addition, we also inject particles with a thermal Maxwell thermal distribution, and follow the distribution of the injected particles, accounting for various radiative, for example, Bremsstrahlung, inverse content, synchrotron, as well as adiabatic expansion losses. So once we have the particles distribution evolved over different times, what we can obviously calculate is the observables, the spectra, and the light curves from the synchrotron radiation from the electron distribution. Also, we can calculate the rotation and dispersion measures that these particles would contribute to the fast radio burst if the burst were to be traversing through this nebula. Once we have all these observables, we can go ahead and try explaining the persistent radio counterparts seen from FRB 121102, the black circles in the middle panel, and FRB 190520B, the diamond markers in middle panel. And we are able to explain the spectra from 0.4 gigahertz all the way to 30 gigahertz, that is GMRT to VLA band, remarkably well using this hypernebula model. In addition, we can also explain the temporal evolution of the rotation measure and the dispersion measure. So once you have this, I'll just steer a little outside of whatever I was talking up until now. There are applications of the hypernebula to high energy neutrinos, to the ice cube detected diffuse background neutrinos, the ones from 1 TeV to 1 PeV. The currently known transients, including supernovae, GRBs, fast blue optical transients, TDBs, they can supply up to 1% of all the ice cube observed high energy neutrino flux. What we showed in this recent work is that the jet termination shock of the hypernebulae that accelerate and inject the protons and electrons into the nebula can interact with the disk photons, thermal and quantized non-thermal photons, and can produce neutrinos through photomasonic reactions. Protons with photons produce neutral pions and charged pions, and these charged pions decay to form neutrinos, and the neutral pions produce gamma rays. The left two panels here show the observed neutrino flux, the cyan, gray, and pink markers by ice cube, and the solid curves here shows the model fit to the observed neutrino flux. and these neutrino flux are produced by the persistent radio, by the nebula that is responsible for the persistent radio source associated with FRB 1202. Another important characteristic of this hypernebula is that the disk photons, the thermal photons from the accretion disk and the non-thermal, thank you, they offer an extremely large optical depth so that the gamma rays, the GeV gamma rays that are produced by the decay of neutral pions, they won't really escape. They will interact, and for example, you can look into the right panel here. The optical depth of gamma-gamma interaction, or the soft thermal photon and the gamma ray photon interaction, is extremely large, so the hypernebula will remain gamma ray faint. And this satisfies the important constraint put by the Fermi integrated gamma ray background on the high energy neutrinos. So, will we be able to see persistent neutrino counterparts from FRB sources? Perhaps, especially if we find an FRB source from a few megaparsec, for example, in M81, say, with a persistent radio source as bright as FRB 1202s, then a persistent neutrino counterpart can also be found with a 10-year integration time with IceCube Gen 2 in the future. So here are some takeaway applications of hypernebulae, which are found which can be found to be presaging common envelope-like events. So operating engines can consistently explain the various properties of FRBs, at least a subpopulation of FRBs, and their associated persistent radio sources, including their luminosity, their spectra, the rotation measures and the dispersion measures, and their time evolution. These sources, they act as signposts to future LISA merger events. They can potentially explain the observed diffuse high-energy extragalactic neutrino flux that is seen by IceCube, the Hubble telescopes. And the final takeaway point is that hypernebulae are plentiful in our universe. They are perhaps even lurking in our current samples, for example, BLA Sky Survey. They are just waiting to be discovered. I'll stop here. I'm happy to take any questions.
Thank you so much. Any question from the audience here?
Very interesting work. Maybe I missed, but could you tell us more about the number density argument? When you fit the IceCube background, then you must have assumed some numbers of hypernebulae, right? So how does that compare with the observed FRB number density?
Alright, so here it is. The volumetric number density of hypernebulae that we consider is around 100,000 per year per gigaparsec cube. And where is this number coming from? This number is coming from the number of observed common envelope events that are found to be associated with at least one compact object. So you have a post main sequence star and a compact object that is undergoing common envelope event. That's the rate that we assume here. As far as the rates of FRB is concerned, the rates of FRB is larger than what can be expected from hypernebulae. So certainly not all FRBs are produced by accreting engines. So that's fine.
Okay, so when you fit the neutrino background, is that can this number density explain the neutrino background?
Exactly.
Okay.
That's the number density that we assume here, and for 100 to 1000 per year per gigaparsec cube, and m dot here is the accretion rate, and for a common envelope like accretion rate of 10 to the 6 or something, 10 to the 7 Eddington, you can actually explain the entirety of the high energy neutrino flux. But if you take a volume average accretion rate of some around 10 to the 6, you would be able to explain at least 25% of the observed high energy neutrino flux by IceCube.
Thank you. Very interesting. Thank you.
Thank you.
Okay, another one quick question from the online people.
Yes, there's a question from Susumu.
Yeah, very interesting. Can we expect maybe at somewhat a lower level of similar processes in nearby ULXs or even SS433 that might be detectable?
Absolutely. The accretion rate of SS433 is around 1000 Eddington. Definitely SS433 is a potential high energy neutrino candidate, but its flux is going to be extremely small that I'm not sure if you can detect a hotspot with 10-year integration with even Ice Cube Gen 2. So if we find a hyper nebula that is close enough, which is 1000 times Eddington plus ULX next source or 10,000 Eddington ULX source, then that could be a potential candidate.
Okay, thank you very much.
But again, it's a volume redshift integrated sample of ULXs will be is what is required to contribute to significant high energy flux. Just individual sources, it will be very hard to detect unless they're extremely close. Yes.
Okay, Navin, thank you. Again, let's send the speaker. Actually,